So, the surface charge density is governed by this way. Here what I have assumed is that no deformation of the double layer, as we said before, and the ions follow the Boltzmann distribution. Now, if I assume that k is very small, so the surface charge density sigma E can be approximately written as eta by A. Now, the total surface charge of the sphere so let us call it QE. This is equal to 4 pi s square sigma s. So, 4 pi s square zeta, so A got cancelled, zeta epsilon E 1 plus kappa A. So, under the assumption this is if this, then what I get is then QE becomes 4 pi A zeta epsilon E. Okay. 4 pi A zeta epsilon E. So, the electric force in that case becomes F E equal to Q E E 0. E 0 is the applied electric field because which is along the direction of the propulsion. So, what I get, this becomes 4 pi A zeta epsilon E E 0. Okay. Now, if U E is the velocity of the particle relative to the liquid, then the drag experienced by the particle is F d equal to 6 pi mu A u e. We can call this is as the Stokes drag basically, because only the simple form will get under the linear Stokes flow. If there is a flow separations and recirculation formation, then this is no longer valid. So, here of course, fluid velocity u e is quite small, that means the Reynolds number basically has to be lower than 1. So, which happens in the electrophoretic situation. So, Stokes drag, one can assume this formula. So, the balance of forces yields F e minus F d equal to 0. So, what I get is u e is basically 4 pi A zeta epsilon E E 0 by 6 pi mu A. So, that means this become 2/3 epsilon zeta epsilon E, of course, epsilon E. This is the electric permittivity of the fluid, zeta E 0 by mu. And the mobility, what we already defined, is equal to, let us call this as mu e, is u e by E 0 per unit electric field. So, this becomes 2/3 epsilon E zeta by mu. So, this limit which is called the Huckel solution. Huckel solution for the electrophoretic velocity. Velocity valid for thick Debye length. Let us write that valid for so now here we have not talked about anything about the migration of ions and movement of ions, electromigration of ions or other kind of things. Now, in the similar manner, we can also have a electrophoresis for thin Debye length. So, now when we come to these situations for thin Debye length, so there what we can talk about that instead of Debye length lambda, which is k inverse, is so we can talk about a flat surface. Instead, the curvature can be up, may not come into picture, because just outside the Debye layer, the flow field is just the balance of the shear stress and the electric force. Okay. So, the screening cloud is confined to a thin layer close to the particle, and the fluid outside the Debye layer can be considered to be electrically neutral. In that case, the curvature effect of the particle can be neglected, and the electrolyte is considered to flow past a planar surface under an external electric field tangential to the surface. So, the conservation of momentum is basically the shear stress and the electric body force, and the Poisson equations can also be written as y is of course is the normal direction. So, that means we have, say, this is the particle. So, let us talk about y. In this case, of course, here we have taken this is the surface as flat. So, because of k is very, very thin. So, locally we can say that only the normal gradient is important. So, the Poisson equations can be reduced to this form, epsilon e d2 phi dy2 equal to minus rho e. So, if we now write from here that mu d2u dx2 by dy2. So, that means we are writing d2 ux, okay, x direction, y2 equal to epsilon e E0 d2 phi dy2 from this momentum equation we just. So, again we assume that the fluid velocity far away from the particle surface is ux equal to minus ue, which is analog to the case in which the particle have a velocity ue relative to the fluid. So, that means we are assuming the fluid particle is stationary and fluid is approaching the particle with a velocity minus ue. So, we can impose the boundary conditions as this: y tends to infinity, that is far away from the surface of the particle, y tends to infinity when we are away from the surface of the particle, that is well within the electrically neutral fluid, we should have phi equal to 0. Ux is coming to be minus ue, because this is the opposite direction fluid velocity we have taken. No gradient for phi, no gradient for u, and on surface of the particle we should have phi equal to zeta and ux equal to 0. So, now if we integrate this equation, so what we get is mu integrate with respect to y, so dx dy equal to epsilon e0 d phi dy, and we apply the infinity condition, these conditions, these two conditions, so we get the constant out. So, constant is 0. Now, further integration, we get epsilon e0 by mu phi plus b. Now, what we have is y tends to infinity, so ux equal to minus u and phi equal to 0. So, this implies b equal to minus ue. Okay. So, that means what we get is ux equal to epsilon e0 by mu phi minus ue by the infinity condition. Now, on the particle surface on y equal to 1 or y equal to 0, we are assuming the measuring these y from the surface, show y equal to 0, what we have is ux is 0 and phi equal to zeta. So, this gives you ue equal to epsilon e0 zeta by mu. So, which is nothing but the Smolchowski velocity. Okay. So, epsilon e0 zeta by mu, which is the Smolchowski velocity, that is the usual electroosmotic velocity when you have a thin double layer is formed. So, what we found is that the electrophoretic velocity of the particle varies from 2/3 epsilon e0 zeta by mu to epsilon e0 zeta by mu as in the limiting situation. This is for the very thin rather thick Debye length, that means k is very small, and this becomes for the thin situations, and the electrophoretic mobility or here velocity, it does not depend, this in these limiting cases are independent of the Debye length. And also note that both the Huckel and these Smolchowski velocities are independent of the particle size. So, thus in classical electrophoretic separation, nanoparticle differing in size is only possible if the Debye length falls into a region where Debye length is in order 1. So, that is why these see what it says this from the limiting situations, that when k is less than 1 or k is Debye length is thin or thick, you have the mu e is independent of size A. So, for shorting on the basis of particle size, k should be of order 1. So, that means k should be of some comparable value. Okay. So, that is why we need now a formula or a expression for mu e, which depends on the which varies with k. Okay. So, to do that, the first analysis was by Henry back in 1931. So, Henry's model is very simple situation. So, Henry assumed that the ions are obeying Boltzmann distribution and also the Debye-Huckel approximation, and through that a closed formed solution was obtained. The distortion of the double layer was neglected, and the electric potential assumed to be a linear superposition of the external electric field and the double layer potential that arise due to the movement of the ions under the equilibrium Boltzmann distribution. So, these Henry model are discussed in several articles, several books. One of these is the Hunter, which is a very fundamental books. So, I am not going into details of that. So, basic idea is that you divide the electric potential into two. One is the double layer potential psi, another is the external electric potential phi. Okay. Now, the psi satisfy the Boltzmann, rather Poisson-Boltzmann equation. So, under Debye-Huckel approximation, one can obtain that a form like this, and this is by the assuming that the ions are obeying the Boltzmann distribution. So, we get a form of this psi governed by this way, and the Stokes equation, which describes the fluid motion. If you take the curl of that and get rid of the pressure and all, so through some simplification one can obtain the velocity component governed by this integral form, elliptic integral form, where zeta is given by this way. This is the thing. So, electric external electric field, if I call it is in a reverse way. Now, here phi is the in this portion we have taken phi as the electric potential due to the externally imposed electric field. So, it satisfies the Laplace equation. If I the insulated particle, that means you have a constant electric potential on the surface of the particle. So, you have del phi del r equal to 0, and at the far end it approach the del phi del z approach the minus E 0, the imposed electric field. Now, if I solve this, we get the form of phi is given by this way. Okay. Now, the Poisson equation for the Doublelayer potential is governed by these equations. So, now if you do some careful manipulations and all, so one can obtain the force component Fh, the hydrodynamic force, and Fe, the electrostatic body force, and the which is the surface charge density, which can be obtained by the from the psi, and the electric field, which are the Ez along the direction along the Ez, basically direction of the particle motion, or which is the same as the electric field direction. So, can be written as E theta sin theta, E r cos theta. So, since the E theta has no component for psi, only phi will have, and psi is only function of r. So, you get this Ez in this manner, and with some manipulations and all, Henry come to the a closed formed solution for the electrophoretic velocity governed by this way, where f kappa a is the called the Henry function. Now, obviously, this UE is depending on the Debye length kappa a. There is no doubt about it, and this kappa f kappa is governed by this way. So, this is referred as the Henry function. Now, the electrophoretic mobility is mu e E 0. Now, if we plot this f kappa a for low to high kappa a values, so we will find that if it is low, it is becoming 1, and so that means you get back the Huckel limit, and if it is high, kappa is very large, you get 3 by 2. So, that means you get the Smolchevsky limit. So, basically f kappa takes this form. So, that means it is 1, close to 1, when kappa is very small, and it is asymptotically merging to 3 by 2. So that means we get back the limits, that is the small here this is the Smolchowski velocity, electrophoretic velocity, and this is the Huckel value, Huckel solution for thick Debye length. So this is the Henry model, and it varies with the remaining portion. This f kappa is depending on the kappa. Now, in the Henry model, as stated before, is assume that the ions are not have no electric osmotic flow of the ions are neglected, deformation of the Debye layer around the particle is not considered, ions are obeying the equilibrium Boltzmann distribution, that means the electromigration and convection effects are not taken into account. So, these are the drawbacks of the Henry model. Now, the second remedy was made by the several other authors. One of these in a very systematic way is OBrien and White in 1978. So, one of the way of solving the electrophoretic problem is by the perturbation analysis. So, perturbation analysis based on the weak applied electric field. So, applied electric field is taken to be very weak enough, so that you have a very first order negligible distortion of the double layer. So, that means this is the 0 superscript 0 is the equilibrium, and due to this applied electric field you have a distortion is this is the next term. Okay. So, now if you substitute in the equation and neglect the higher orders for this approximation or these error terms, so deviation terms, so you get a series of ordinary differential equation. So, these ordinary differential equations, and of course, this 0 are governed based on the small Boltzmann distribution of ions can be assumed for the zeros, and it obeys the Boltzmann distribution because we assume a equilibrium situation for the in the beginning and a first order distortion. So, through that the solutions was obtained, and that solution differs from the Henry mobility by a large extent, particularly when the zeta potential becomes high. That means, where the Debye-Huckel no longer valid, and also when the Debye length is thick. So, that means Debye length is not thin. So, that means K is of order 1. So, in that case the deformation or of the double layer or the double layer polarization become very important. So, here is the comparison with the computed solutions and all this model solution. Henry Oshima is another model, then Weizermann. Weizermann is the similar as the OBrien White. So, these results Weizermann or OBrien White are pretty accurate with the computed solution, that means solving the full set of governing equations as discussed in the very beginning. And but the Henry model, which is the linear model, that deviates to a large extent, particularly when Debye length become thick and zeta potential is high. Now, when the Debye length is not thin, then the deformation or the Debye layer polarizations become very important aspects. See which way we have defined is that the somewhere, no. So, which way we have discussed is this Doublelayer polarization is that, see, if the Debye length is not thin, so what will happen is that the ions, as we move away from the particle, will be loosely connected, because the shielding effect is not strong as we go away from the particle, surface of the particle. So, this loosely connected ions, imbalanced ions, when there will be an applied electric field, so it will move in the opposite direction to the direction the particle is moving. So, it is negatively, so there will be a negative ions will be surplused, and that will move or rather positive ions will be surplused here. So, these particle ions will be moved, and then in that process there will be a electroosmotic flow, and as well as the due to the movement of the particle. So, there will be a wake formation. So, the ions will be pushed backwards, that is the downstream direction. So, in that process there will be a oppositely directing electric field will be developed. So, these interactions of the double layer polarization and also the relaxation effect, which is important when zeta potential is high, and their interaction with the electroosmotic flow of the imbalanced ions become very important, and that is only possible to capture through the model based on the Navier-Stokes equation without doing any neglecting the terms, neglecting some effects, like in the first order perturbation analysis, where the nonlinearity is not completely neglected, but it is taken only up to the first order aspect. Now, most cases for finding the electrophoretic velocity and all, the first order analysis found to be quite okay, but when you want a precise measurement of the force and flow pattern and all, so and also we will talk in the next lecture about the electric polarization. So, in those cases the first order perturbation analysis is not good enough. Though here you see the force variation of the electric force or drag, which are the same. So, with the Debye length. Now, see, there is a all of a sudden there is a formation of a kind of kink or pattern change, that is because of the Doublelayer polarization at this kind of values of kappa A. So, also we see the as zeta potential of the particle surface potential is increasing, the electric force as well as drag is also increasing, and also the electric field, variation with the electric field, which is somewhat linear up to this range of electric field, and the form of the drag is showing, but the pattern, the variation of k kappa A different electric field may not be similar. This is the streamline pattern, no doubt it is looks like a Stokes flow. The streamlines are forming a linear Stokes flow kind of things, no separations and eddy formation. And this is the showing the counter ion distribution. So, it is negatively charged, show positive ion distribution around the particle. So, this is the particle. So, what you can see is the deformation of the double layer is quite evident, and this is the charge density distribution. So, that means here rho e, basically the scaled rho e, this is the near the particle. So, if we move away from the particle, rho e is 0. So, that is why no contours. So, rho e is non-zero only near the close to the particle, and this is the electric potential line. Again, is a ring structure is forming. There is the pressure contours. So, particle is moving. So, induced pressure is developed near the particle surface. So, we will continue to the next lecture on induced electric field formation when the particle is considered to be a dielectric particle. Thank you.